Assalamu alaikum. The title of our course is Linear Control Systems. However, we have still not formally defined the word linear. So in today's lecture, we shall explain the word linear. We shall also obtain mathematical model of some nonlinear systems, and then we shall learn how we can linearize those mathematical models. So any function or a system or an operator which satisfies these two properties, that is homogeneity and superposition, that function or system or operator is called a linear function, a linear system, or a linear operator. The homogeneity property for a function states that if we scale the input to that function, the output is also accordingly scaled. That is, f of alpha times x is the same as alpha times f of x. The superposition theorem states that if we apply a linear combination of the inputs to a function, then the outputs are the same linear combination of the outputs corresponding to that particular inputs. Sometimes these two properties are combined in a single property and is written over here. That is, f of alpha times x1 plus beta times x2 is the same as alpha times f of x1 plus beta times f of x2. Similar to the functions, a system is a linear system if it satisfies the superposition theorem. That is, consider this system with u as the input to the system and y as output of the system. So let's consider that if we apply an input u1 to the system, then output is y1, and for input u2, output is y2. If we apply a linear combination of these two inputs as an input to the system, then the system will be a linear system if the output for this particular input is the same linear combination of these two outputs, that is alpha y1 plus beta y2. So let's explain these concepts with the help of some examples. We have a function y is equal to f of x, which is equal to 2 times x. So this function is graphically depicted over here. On this horizontal axis we have x, and vertical axis the function f of x. So for this particular function, if we have f of x1 plus x2, that is equal to 2 times the input to the function, that is 2 x1 plus x2. If we expand this bracket, it is 2x1 plus 2x2, which is the same as f of x1 plus f of x2. So superposition theorem is satisfied for this function, therefore this function is a linear function. Next, take example of this cosine function, which is graphically depicted by this figure, and let's check the superposition theorem, applicability of superposition theorem for this function. So we know that cosine of x1 plus x2 is not equal to cosine of x1 plus cosine of x2. So superposition theorem is not satisfied for this function, therefore this function is not a linear function. Similarly, if we talk about this function y is equal to x square, superposition theorem is not satisfied for this function x1 plus x2 whole square, that is not equal to x1 square plus x2 square. So this function is not a linear function. Let's talk about this operator d by dt. What about this operator? Is it a linear operator or a nonlinear operator? So we can see that d by dt of a linear combination of two inputs x1 and x2 is equal to alpha times dx1 by dt plus beta times dx2 by dt. So for this operator, superposition theorem is satisfied, therefore this is a linear operator. What about this operator? Similar discussion can be carried out for this operator, and we can see that again this superposition theorem is satisfied for this operator. Therefore this is a linear operator. So remember that for functions, not always a straight line will represent into a linear function. Let's talk about this function, that is y is equal to 3x plus 2. This is equation of a straight line. However, this function does not satisfy the superposition theorem. Let's check it over here. If we apply an input x1 to this function, then y1 is equal to 3x1 plus 2. For input x2, we have y2, which is equal to 3x2. Here it is x2 plus 2. And if we apply a linear combination of x1 and x2 to this system, then the output is 3 times x1 plus x2 plus 2, and this is not equal to y1 plus y2, that is this plus this. This is not equal to this one. So superposition is not satisfied for this function. Therefore this function is not a linear function. So the point here is to clarify that not always a straight line will represent into a linear function. However, we can easily transform this function into linear function by change of coordinate systems, change of variables. Therefore such straight lines can always be transformed into linear systems, and therefore we shall also consider this function as somehow similar to a linear function. Some common nonlinearities which are there in many physical systems are saturation. Saturation nonlinearity is described by this graph. Up to a particular range, if we increase an input to that function, input to that system, the output is accordingly increased. However, after that point, the output saturates, and an increase in x is not resulting into a proportionate increase in the output. So this nonlinearity is called saturation nonlinearity. This is very common in electronic amplifiers and many other systems. Another nonlinearity is dead zone. It is graphically represented over here. For a particular range of input, there is no output to that nonlinearity, and after that an increase in x results into proportionate increase in the output. This nonlinearity is very common, for example, in motors, in pumps, that is up to certain voltages these motors and pumps do not respond, and after that an increase in the input voltage results into the increase in the output torque of that motor. Another nonlinearity is backlash, which is there in gear systems. That is ideally what should be the case. If we rotate the input gear, the output gear should start rotating. However, that is not the case. Generally, there is a small distance between the teeth of the two gears, so even if the first gear starts moving, the output gear does not move. So this nonlinearity is called backlash nonlinearity. A similar nonlinearity is there in magnetic circuits, which is called hysteresis, and that is also similar to this nonlinearity. In this course, we shall be mainly dealing with linear systems. So how to obtain a linear approximation of nonlinear system? For that purpose, we shall describe an approach that is called Taylor series approximation of nonlinear functions. So the concept is illustrated in this figure. We have a nonlinear curve shown by this black curve, which relates the input x and f of x. We want to find a linear approximation to this nonlinear function. So this nonlinear function can be linearly approximated by this curve. this straight line. So we can see that near this operating point, near this working point, this blue line, straight line, is a good approximation of this curve. However, if we deviate away from this operating point, there is a significant difference between the nonlinear curve and the straight line. So this linearization technique is applicable if we are working near the operating point. And the approach is Taylor series. You already know nonlinear function can be expanded by a Taylor series. F of x is equal to the function evaluated at the operating point plus the derivative of that function with respect to x evaluated at the operating point multiplied by x minus x naught plus some higher order terms, the square term, and next we will have a cubic term, and so on. We see in this expression that if we are near this operating point, then x minus x naught will be small and its square will be still smaller. The cubic terms will be further smaller, so we can just omit these small terms, and therefore f of x minus f of x naught, this brought to the left hand side, is approximately equal to this term, that is, the higher order terms are omitted. This is only approximately valid because we have omitted the higher order terms. And then we can rename this difference as another function of x, that is delta f of x. This is named as m, and x minus x naught is called delta of x, which is a linear function. This function is a linear function. Let's apply this knowledge to some functions to demonstrate the Taylor series approximation. We have a nonlinear function given by f of x is equal to 5 into cosine of x. This nonlinear function is represented by this curve, and we want to linearize this function at about this operating point, that is x is equal to pi by 2. And we can see from this graph that this blue line, which is linear approximation to this nonlinear curve, is matches the original curve for points near the operating points. However, if we move away from the operating point, then there is a difference between this linear graph and this actual curve. So this linearization technique is valid near the operating point. We have already talked about Taylor series, so let's apply that. F of x naught for this function is f, the function evaluated at the operating point, cosine of pi by 2 is equal to 0. Therefore f of x is nearly equal to f of x naught, which is 0, plus the derivative of that function with respect to x. The derivative of this function with respect to x is cosine of x, that its derivative is minus sine of x, and evaluated at the operating point multiplied by x minus the operating point, which is pi by 2. So cosine of x is approximately equal to this expression, and therefore f of x is equal to 5 times delta x, because sine of pi by 2 is 1, so 5 comes from here, so minus 5. Here it should be minus 5 into delta of x, where delta of x is equal to x minus pi by 2. So we have approximated this nonlinear function by a linear function, that is this nonlinear curve by a straight line. Let's take another example to demonstrate the linearization of dynamic systems. We have an electrical circuit over here, and here this resistor is nonlinear resistor. Generally, you know that for a resistor, the current in the resistor is proportional to voltage through the resistor, voltage across the resistor. However, this resistor is a nonlinear resistor for which the current and voltage are related by this expression. That is, IR is equal to 2 times E exponential of 0.1 into VR. Have you ever seen such a resistor in your previous courses, this nonlinear resistor? Yes, diode. The equation of the diode is governed by such equation. So here this nonlinear linear resistor can be anything which satisfies this equation. For example, it can be diode. This equation can be rewritten in this form by taking the natural log of both sides and then by rearranging the terms. So VR is equal to 10 into natural log of half IR. The mathematical model for this system, electrical system, can be quite easily obtained by applying Kirchhoff's voltage law. That is, sum of voltage drops is equal to sum of voltage rises. This is the voltage drop across this inductor, voltage drop across this nonlinear resistor, and then voltage rise, and this voltage rise and written on the right hand side. In this differential equation, this term is causing nonlinearity, so we would like to find its linear approximation by using Taylor series. So we want to find linear approximation of this nonlinear function. We have already talked about this Taylor series approximation. So f of x, this is f of x minus f of x naught, the function evaluated at the equilibrium point, operating point, that is equal to derivative of that function with respect to the input variable, derivative of that function with respect to the current, the input variable, evaluated at the operating point, multiplied by delta I, that is x minus x naught. So we can take the derivative of this expression with respect to the current, that is 1 over I, and evaluate it at I equal to I naught multiplied by delta I. If we substitute I equal to I naught, we get 1 over I naught into delta I. That is, this is approximately, here it should be approximately equal to this expression. So now the differential equation which describe the nonlinear circuit, here this term, this nonlinear function, can be approximately described by this expression. Here if we bring it to the right hand side, we had this equation. So let's take some numerical values, that is L equal to 1 and I naught equal to 14.78. then this equation is transformed into this equation. We have simply substituted these numerical values. This comes out to be 20, this comes out to be 20, which is cancelled out over here, and we have this term and this term and the right hand side, which is a linear differential equation. We can even write it in Laplace domain by taking the Laplace transform of this equation, and that is described by this equation. Remember that the transfer function can only be obtained for linear systems. For nonlinear systems, we do not talk about transfer functions. Here we have obtained a linear approximation to that mathematical model, and then we worked out the things in Laplace domain to obtain the transfer function. So up to this point we have talked about mathematical modeling of physical systems. Mechanical systems were discussed in much more details. We also talked about electrical systems, liquid level systems, pneumatic systems, and then we learned how to obtain a linear approximation to nonlinear mathematical models. In the next lecture, we shall inshallah talk about the transient behavior of the systems, and we shall talk how we can describe the specifications of the systems that we want to achieve.